Welcome to our next section, the application of derivatives, applied optimization. Applied optimization. To optimize something often means to maximize or to minimize some aspect of it. For example, what are the dimensions of a rectangle with fixed perimeter having maximum area? What are the dimensions for the least expensive cylindrical can of a given volume? How many items should be produced for the most profitable production run? We will use derivatives to solve such a variety of optimization problems in business, mathematics, and economics. This ties in basically what we've just finished with. This ties in with critical points. And it also ties in with maxima, absolute maxima, and minima. We are going to still do what we did before. You're going to take the first derivative and put it equal to 0. And we're also going to use what we did before, our first derivative test. So basically, this is one of the applications. That's a D, guys, the derivative test. This is an application of what we did before when we were just doing functions and I was having you practice it. Now you're going to use it for real life examples. Now I've got the problem solving strategy here. Please refer back to it when you need to, but if you look at it, you can see how this is going to work out of it. So first, we're going to draw a picture and name the variables and constants. Again, I want you to label the crap out of your picture so that we know where everything is. Then we're going to use two things that I find so important. One is called a constraint equation. This outlines the limitations in the problem. Then you're going to have an objective equation, and this is what you need to find. Okay, I want you to substitute the constraint equation into the objective equation. We're going to take the first derivative take the first derivative and put it equal to 0, and then we're going to draw your f prime bar and do the first derivative test. So it does have a little bit different what we did before, but now you'll have a method in which to do this. All right, so let's try a couple problems. I'm going to start very simple, and I know especially with this first problem that you could probably figure out and guess it. So here we're going to be maximizing a product, okay? The sum of two numbers is 12. Find the numbers if their product is at a maximum. Well, before I do this the calculus way, because I'm only going to want all of these as only a calculus solution, is I want let's see how we can do this intuitively and come up with the answer before we do this. All right, now you're not going to be able to do this with all of them, but I'm going to set a chart here, XY chart. And we know the sum of two numbers is 12. So I'm going to do some numbers here. So I got 0 plus 12. And we want to find where the product is a maximum. Then I've got 1 plus 11, 2 plus 10, 3 plus 9, 4 plus 8, 5 plus 7, 6 plus 6. And then if I keep going, 7 plus 5, I'm going to repeat all these numbers. Now if I did a product for all of these, the product of those two is going to be 0. The product of those two are going to be 11, 20, 27, 32, 35, okay, and then 36. Now if I repeat this, this looks like this is going to be our maximum. It looks like our two numbers are going to be 6 and 6 because that's where the product, right here's the product, is at a maximum. So you're like, well, we're done. I don't have to use a calculus solution. But I'm trying to show you the method because they do get much more difficult than this. So let's get started. First, we're going to talk about our constraint. So our constraint is meaning what we have to have in our problem. What is holding us back, if you will? What do we have to have? And the only thing we have to have in this problem is that the sum of two numbers has to be 12. That's our constraint. So let's use x for the first number, y for the second number. So if I add them up, I know they have to be 12. That's our constraint. We have to have that happen. Our objective is that we have a max product of these two numbers. So this is what we need, okay? This is what we need to have happen. This is what they want us to solve, okay? Is that they want our product to be at a maximum, okay? Well, I know that if they want the product to be at a maximum, my equation would be the product would be x times y. So that is what we need to have happen. Now, what you're going to do next is you're going to take this constraint equation and solve for one of the variables so that we can actually place it here. So I'm going to make it easy and solve for y, and when I do, I have it's 12 minus x. And if y is 12 minus x, I can take this and actually put it in here into our objective, because now we've put our constraint that we have to have into our objective. And it makes it all one variable. So if I go through and do the distributive property of 12x minus x squared, and I come up with this as the product. Now, here's where the last chapter we did ties in. If I want to find a max, if you think about this, is a parabola, and it's a parabola that's shaped downwards. Okay, this is what it looks like. That's what it looks like. And basically here, this is where our max is going to be, because this is got a negative x squared. So what we're going to do is put this equal to, we're going to take the derivative, p prime, and put it equal to 0. So I get 12 minus 2x, and it's going to equal 0. So then I'm going to solve for that. 2x equals 12, x equals 6. So I found the first number to be 6. Then I want you to come back over here and plug it into this one. Y is 12 minus 6, so y is going to equal 6. So we came up with our answer so far, but we have to test it, is I believe the maximum is going to be when x is 6 and when y is 6. There's our answer. So before you can finish this, we have to test this to make sure that it is a maximum, and we're going to use our p prime bar at 6. Go here to your derivative like we used to, right here, or actually you could do it here in factored form, would probably be nicer. And no, I apologize, that's not what we want to do at all. We want to go to the derivative, so that's this right here. Okay, so what we're going to do is plug in numbers to the left of 6 and to the right of 6 to see what if it's going to be at a maximum. So say I used 0, for example. If I plug a 0 here, I'm going to have 12, and I look at it, well, that is positive. 12 is positive. Now if I put a 7 in here, this would make a negative 14. This would make it negative. So using my first derivative test, I see that this is a max. So this can be our answer. We did find the product, the sum of two numbers, that their product is at a maximum. Alright, so that kind of gives you the setup of how the problems are going to be. Now let's look at the next one. Now this one's a little bit different, but we're going to still kind of set it up. This one is minimal cost. Alright, so we're looking at minimal cost. The field of area 6,000 square feet is to be enclosed by constructing a fence costing $3 per linear foot on 2 parallel sides and using a stone wall on $5 per linear foot on the other 2 parallel sides. Well, before we start doing this, I noticed 2 parallel sides and 2 parallel sides. So this is rectangular or square or whatever you want to look at it. So we don't know what it is, so I'm just going to draw it like this, that I've got 2 parallel sides going here. Alright, so there's a stone wall on one side, okay, and it costs a little bit more per linear foot. Well, first of all, let's label this. We got a field of area 6,000 square feet, so I'm going to put this in here. This is 6,000 feet squared. And I always label the crap out of everything to make sure that when we go to do our problem, we can see where everything is. And it's enclosed by constructing a fence costing $3 per linear foot on 2 parallel sides. So let's call this the $3 per linear foot is on these 2 parallel sides, and we'll call this side X. So it's going to cost us $3 per linear foot, and these two are the same, so I can call it X. And on the other 2 parallel sides, we're going to use a stone wall that costs $5 per linear foot, and we'll use Y for this. It's $5, and we'll call this Y also on the other 2 parallel sides. Now they want us to do is find the dimensions that will minimize the cost. Now this will come in handy a lot, because sometimes you want to enclose a certain amount and you want to know what would be the best dimensions so that this is not going to cost you as much. So let's set up our 2 equations. The constraint is what is in the problem that we must have, and the cost per linear foot is going to be our constraint. The other constraint we have is also the area. They said it has to be 6,000 square foot. Alright, So you're like, well, what do I put in the constraint? Well, if we want to find the dimensions that minimize the cost, this is what we need to have happen. So this is going to be right here, our objective. The constraint is basically the area in this case. So if I did the area of this, it would be x times y equals 6,000. So it's 6,000 square feet is our constraint. Our objective is to minimize the cost. So here's where we're going to use the cost of both of those sides. So if I'm doing a cost and I'm talking fence, I'm really talking perimeter because I'm going all the way around this. So instead of calling it perimeter, we're going to call it a cost equation because we're going to go around and do the perimeter, but also I'm going to do the cost. So here I've got two sides of x, all right? I have two sides of x, and the two sides of x are going to cost me $3 per linear foot. So I'm going to say, okay, $3 times those two sides, plus now I have two sides that are y, and that's going to cost me $5. So there's our cost equation. That's our objective, is to minimize the cost. So if the cost is going to be 6x plus 10y. All right. Now we're going to go over here to our constraint, and I'm going to solve for y just to make things a little bit easier. So I'm going to do this, and I'm going to replace this in the y spot of this equation right here. I'm going to put it right in that spot. So the cost equation is going to be 6x plus 10 times 6,000 over x. Now I'm going to try to simplify this a little bit. So I got the cost is 6x plus 60,000 over x. Now we're going to go through and do the first derivative so that we can put this equal to 0 so we can find the minimal cost. But before I do this, I'm going to rewrite this cost equation a little bit so that you can do the derivative easier. So it's going to be 6x plus 60,000 x to the negative 1. Now when I do C prime, it's going to be 6 minus 60,000 x to the negative 2, and then we're going to put that equal to 0. Now I'm going to rewrite this back the way that it was. So I have 6 minus 60,000 over x squared has to equal 0. And this is what kind of confuses people when they get to this point. I'm actually going to take this whole term and move it over to this side over here. So I'm going to have 6 equals 60,000 over x squared. And when I get it this way, I'm going to cross multiply. So I have 6x squared equals 60,000. Divide by x. I mean by 6, I got x squared equals 10,000. And then when I take the square root, I have x is going to equal 100. Now it's really plus or minus 100, and we're talking feet, so I'm going to label this. But the negative would not make sense in this case because we're talking about area and length of fence. So now we know that these two sides of our fence right here is 100 feet. Okay, whoops, not that side. It's the other two sides. I just solved for x. So let's get rid of that. Okay, so it's going to be right here, 100 feet here, and 100 feet here. Now I want to find the other two sides. So I'm going to put 100 in for x right here. So I got y equals 6,000 divided by 100. So y is going to be 60 feet. Which, if you think about this, this makes a little bit of sense because if you're trying to minimize the cost, the stone wall costs more than it does the other two sides. So it does make sense that those are going to be shorter to minimize the cost. So it looks like, from what we found, that the dimensions of our fence or what are we going to do of our area of this shape is going to be 100 feet by 60 feet. So that looks like that's what our answer is going to be. But you don't know until you test it, so you always have to test it. So we're going to do our C prime bar here because we want to minimize the cost. We found x to be 100, and now we're going to go to the left or right. So find where it's best to check it out here. So here's our first derivative, and we put it equal to 0, so I'm going to plug it in. We can use this one right here if you want to, or this one right here if you want to, doesn't matter. So if I go to the left of 100, we can use, you can't use 0, but you could use a 1 if you wanted to. And if you did this, it would be negative. And to the right of 100, you can use 200, you can use 300, whatever you want it to look like this. It's going to turn out to be positive. So this does go like this. This is a minimum, so this is the minimum cost. You just tested it. Now, I want to say one more thing before I complete this video. If you solve this constraint for x, we'll say, so you have x equals 6,000 over y and plugged in the x spot, if you would have gone through and done all this, you would have solved for the 60 and then you would plug it in to find the 100. So you and your neighbor could do the same exact problem but solve for something different, just depending on what variable you want to use. And you don't have to use x's and y's like I did. You could use w and l's for length. I just use that to make it look easier. Okay, well that completes this. I'm going to do more videos with other problems